All right, welcome everyone. It's my pleasure to introduce Nick Cox-Steib, who will tell us about perturbing ideals in arbitrary Noetherian local rings and the m-adic continuity of Hilbert-Kunz multiplicity. Nick.
All right, thank you, Sean, and thank you, Eloisa. All right, yes, I'm talking about perturbing ideals in arbitrary Noetherian local rings and m-adic continuity of Hilbert-Kunz multiplicity. I'm going to start by telling you about Hilbert-Kunz multiplicity. Maybe you already know, but this will serve as a reminder. Okay, so let's let R be a Noetherian local ring and suppose that it has positive characteristic. In characteristic P, the Pth power map is a ring endomorphism, right? It respects addition. Which, right, is very special. And so this endomorphism has a special name. It's called Frobenius. And I'm going to use this capital F to denote it. And in general, F to the E, or F with an E, superscript here, is the eth iterate of Frobenius. So it's the P to the E power map. Okay, so given an ideal in R, I can extend this ideal across this map and get a new ideal in R, right? That's called the Frobenius power of I. And it's written like this: I bracket P to the E. It can be described sort of more conveniently in this form. So if I have generators F1 through FC, I bracket P to the E is the ideal generated by F1 to the P to the E through FC to the P to the E. Okay, let's see. I need one more definition. This won't come up for a moment, but later on I do use this term. R is F-finite if the Frobenius map is a modulo finite map. Okay, so let me just say a couple things. I've left some space in here for me to make notes so it feels a little more interactive. But the existence of Frobenius is really sort of theoretically interesting, right? Every characteristic P ring comes with this endomorphism. They're all compatible with one another. It gives you a powerful way to analyze rings in characteristic P, and I'll talk a bit more about that in a second. But it also comes with sort of, it's a double-edged sword, right? It also is responsible for the phenomenon of inseparability, which is a huge headache often, right? So in characteristic P, so you have things like this, right? There's only one Pth root of unity, things like that. It's a headache, but as I said, it's a double-edged sword. So this all really starts with some work of Ernst Kuntz, 1969. R is a Noetherian local ring, dimension D, and positive characteristic. Kuntz showed that the properties of Frobenius detect important properties of the ring, like smoothness properties. Kuntz's theorem says that R is regular if and only if the Frobenius map is flat. Basically, anybody who studies characteristic P things, many of the talks you've seen that are talking about characteristic P things probably begin with this result. It's extremely important and interesting. And in the course of proving this, actually, he showed the following. He showed that if E is a non-negative integer, then this length R mod the P to the E bracket power of the maximal ideal is always bigger than or equal to P to the E to the D. P to the E times D, sorry. And that this is an equality for some E, if and only if it's equality for all E, if and only if R is regular. Okay, so interesting. This suggests an idea. Let me just kind of write a little funny arrow. So it says maybe the values of this sequence of lengths so if the values of these the values of the sequence are close to 1, then R is close to being regular in some sense. All right. That's kind of a vague idea, but it can be made a little bit more explicit. And actually, I guess in Kunz's original paper, he thought about this question. In fact, he thought about the asymptotic properties of this and wondered about its limit. It's certainly true that if R is regular, you can show this limit goes to 1, right? This result shows that. But he actually believed he came up with an example where this limit didn't exist. But it turns out he was wrong. Monsky showed that the limit of this sequence exists, and he gave that limit a special name. So this is 1983. R is Noetherian, local, positive characteristic. Say D is the dimension. Then this limit exists, right? This is the asymptotic. Basically, it measures the asymptotic growth rate of these lengths, and it's called the Hilbert-Kunz multiplicity of R. And let me just say a couple things about this real quick. So first of all, actually shows more. You can extend this to an arbitrary m-primary ideal in R and a finitely generated R module. Okay, and actually almost all the results that I talk about today extend in a similar way. At least I think they do. It certainly do for m-primary ideals. I also think they'll extend for modules, but I'm not going to tell you about that because I haven't done it. Okay, so there are a lot of really amazing properties. Hilbert-Kunz multiplicity, it's additive on short exact sequences. There's associativity formula. It's called a multiplicity for a reason, sort of by analogy with Hilbert-Samuel multiplicity. Excuse me. And it actually agrees with the Hilbert-Samuel multiplicity if R has dimension 1, or if we're talking about a ideal generated by a full system of parameters. Moreover, right, sort of the original motivation for looking at this thing is that if it should detect irregularity. And if R is unmixed, it does. I think this is a result of Yoshida and Watanabe that was sort of proven again by Craig Hunicke and Youngwei Yao, but it's known that if R is unmixed, the Hilbert-Kunz multiplicity is 1 if and only if R is a regular local ring. And by the way, this unmixedness condition means there's no embedded primes and it's equidimensional, so no funny business with the minimal primes. All right. Also fascinating to me, I actually came to be interested in this stuff from the perspective of somebody who's like really into numbers. When I started graduate school, I thought I would just study number theory, but so I'm really into specific numbers, and the numbers that are sort of that show up as Hilbert-Kunz multiplicities are numbers I'm interested in knowing more about. So they can be irrational and transcendental, although the proofs of these are from Helger Brenner. They're sort of non-constructive, or at least not as constructive as I would like. So let me say, in that direction, a not so nice property of Hilbert-Kunz multiplicity is that it's extremely hard to compute. Okay, I mentioned that mostly because I'm interested in the values. Let's see, maybe I'll make this a little bit bigger. Also, before I started this, I should have given you a disclaimer. I'm possibly the worst speller in the history of the English language. So if I spell things incorrectly, I don't mind if you correct me, but I also just want to apologize if it offends you. I really don't think that anything can be done about it at this point. All right, so now I'm going to talk about the results in this work. This is from my thesis, and I want to start by telling you the result that motivated me. And to do that, I need some notation. All right, so here's where the perturbation type stuff comes into play. Let's let R be Noetherian, local, and let's say I have an ideal I that's generated by elements F1 through FC, just any generators, not even necessarily minimal. I'm going to write this with this shorthand. So F underbar means just this sequence of elements F1 through FC. And in general, I'll just use an underbar to mean a sequence of elements. It's just a convenient notation. If I take minimal generators of I and I modify them by adding some little epsilons that are in a high power of the maximal ideal. By high power, I mean something that will be explicitly given. I call that an m-adic perturbation of I. So start with I, take its minimal generators, and then modify them by adding something in a big power of the maximal ideal. That's a perturbation. And I use this notation to talk about a perturbation, right? So there are indexes on the F's and the epsilons here. Okay, so if there's a question about notation, please don't hesitate to ask. It's a bit of a nightmare in this business. Let's see. I say a perturbation is small if T is large, but the meaning will be clear from the context. Typically, I'm interested in understanding properties shared by an ideal and its perturbation if T and its perturbations if T is large enough, right? So I'm looking for something like that. And here's some more notation that, again, just ends up being convenient. If M is an R module and I'm perturbing some ideal, let's say we're talking about perturbations of some fixed ideal I, then I use the notation M bar to just mean the quotient of M by IM. And this kind of nasty looking notation right here, M bar sub the perturbation to just mean M mod that ideal times M, right? Okay. The reason for this is just these things show up so much in this paper, it just gets really tiresome writing it all the time. And actually, when it's convenient, I might actually refer to oh my gosh. These guys as perturbations of M bar. In the end, at some level, I'm interested in understanding the relationship between I and its perturbations, but you can phrase that in terms of these quotients, right? So there's not really any danger in doing this. Okay. Let's see, it's been 15 minutes, that's good, that's good. Here is the result that really motivates my thesis work. In 2018, Thomas Polstra and Smirnov, they prove this result that I think is really, really interesting about Hilbert-Kunz multiplicity. So let's take R to be d-dimensional, F-finite, and Cohen-Macaulay. It's a local ring of characteristic P as well. I'm going to circle this. And suppose that I is an ideal generated by parameters. So it's minimal generators that are F1 through FC, and F1 through FC are part of a system of parameters, right? It's a parameter ideal. let's assume in addition that after I complete and quotient out by I, get something that's reduced. This is about the Cohen-Gabor structure theorem, which I'll mention later. Then the Hilbert-Kunz multiplicity exhibits a kind of m-adic continuity with respect to perturbations of I. So what do I mean? I mean, for any delta positive sufficiently close perturbations of I, or of R bar, we'll have Hilbert-Kunz multiplicity within delta of R bar's Hilbert-Kunz multiplicity. So this is what I mean when I say m-adic continuity here. It's with respect to perturbing the ideal you're quotienting out by. Okay, so it's a kind of m-adic continuity. Let me say a couple of other things about this. I think this is really amazing. These are numbers that, for the most part, we just have no hope of computing for them. In most cases, it's really fascinating to me that we can relate them like this. And it's a neat expression of the relationship between an ideal and its perturbations. So let me say a bit more. The T here doesn't depend on the choice of minimal generators. I think I actually make that explicit in the results I prove. And you can actually extend this to M primary ideals. In other words, the Hilbert-Kunz multiplicity of those ideals in these quotients are related like this. I don't know if I mentioned this, by the way. I keep writing fancy M sub R for the maximal ideal of R. The reason I have written sub R is because I'm going to be talking about more than one local ring here in a minute, and it's sort of important to keep those maximal ideals distinct. All right, that's the result that I find so interesting. My goal is to try and drop the Cohen-Macaulayness condition. Okay, so I just go back up here real quick. They're assuming the ring is Cohen-Macaulay and that this ideal is generated by part of a system of parameters. That's a pretty substantial condition on both the ambient ring R and this ideal, right? Systems of parameters are regular sequences in a Cohen-Macaulay ring, right? That's one way to define the Cohen-Macaulay condition. So in order to generalize this, I drop this Cohen-Macaulay condition. I need to find some way to balance that with a condition on I. So there's a bit of work and fussing about that I'm going to do here in a minute. Okay, so that's the reason for that. Let me write this down for you. Okay, so in the Polstra Smirnov results, R's Cohen-Macaulay, I is generated by part of an SOP. And actually this implies right away, of course, that I is generated by a regular sequence. And actually it implies immediately that R mod I is Cohen-Macaulay as well, which ends up being an important ingredient in their argument. Okay, it's not hard to show that some condition on the ideal has got to be necessary, and even being a parameter ideal alone is not going to be enough outside the Cohen-Macaulay case. There's an example at the end of my paper, which if I have time, I can do at the end. But so the idea is to try and balance this, dropping the Cohen-Macaulay condition on R and put that into a condition on the ideal. It basically ends up being some statement about how the ideal relates to the Cohen-Macaulay locus of the ring, or at least that's one way to understand it. So this is actually going to have something to do with the first Cazul homology of the ideal. And let me remind you what the notation is, or tell you what my notation is for that, and give you a little word of warning. All right, I don't think anyone has any questions. If you do, remember, don't hesitate to interrupt. I'll probably see you in the chat if you say something too. But, all right, M finitely generated as an R module. This H1 of I semicolon M here I is an ideal. It denotes the first Koszul homology of I with coefficients in M. So the question is the T easily constructed in the Polstra Smirnov result? It depends on quite a few things, but yeah, it depends on quite a few choices, but it can be explicitly constructed. Yeah, that's right. I'll try to be clear about what T depends on in my result as well. It depends on like a whole bunch of Art and Rees numbers, essentially. Okay. It's a good question, very interesting question. I suspect that all of these choices of T in my paper at least can be improved probably. All right, so I use this H1 to denote the first Koszul homology. Let me tell you what that means. I really mean you take the Koszul complex on some minimal generators for I, tensor with M, and then take the first homology. Since the ring is local Noetherian, different choices of minimal generators give isomorphic H1s. That's extremely useful and important. It's not always true without these assumptions. But I use that sort of in an absolutely indispensable way. So probably taking these results where that kind of thing doesn't apply might not be possible. And I've accidentally left this in. I meant to write it myself or here during this while I told you about it. But this construction of H1, it does not commute with localization necessarily. So the reason for that is that if I choose minimal generators for I and R, those don't necessarily become minimal generators when after I localize, right? Maybe I localize and then I could be generated by fewer elements. And so if I compute this H1 and then localize it, it's not going to be the same thing as if I computed the H1 in the localization. So just keep that in mind when I state the condition of my result. This has been actually a source of confusion for me several times, and I keep thinking I find counterexamples and need to always remind myself. Okay, so the condition that Thomas and Ilya put on I actually can be phrased as this H1 vanishing, right? That's equivalent to I being generated by a regular sequence. And they also have, as I said earlier, that R bar is co-Macaulay, and in particular, it's unmixed, it's equidimensional. So they use both those facts in their proof. All right, here is the generalization I end up with from my paper. And I'm going to tell you the generalization, then I'm going to start telling you about how I prove it. It's really a matter of how much time I have. Let R be Noetherian local, positive characteristic, and F-finite. I needed to keep the F-finite in this condition. The methods just don't work outside of that case. Let's take I to be an ideal and assume that the dimension of R mod I is at least 1. I'll say a bit about that in a second. Maybe it seems like a strange condition to make right now. Let's assume in addition that after I complete the quotient out, I get something that's equidimensional. It's this. And this third condition, I guess I'm going to talk about first. Let's assume that the dimension of the nil radical of this quotient is less than the dimension of R. It's like a generic reducedness condition. That is just all about Cohen-Gaber. I need it to make this argument work. So in order to get Cohen-Gaber to hold, the Cohen-Gaber structure theorem to hold, I need those conditions. And then the second condition, this is the condition on I, that the dimension of this Koszul homology as an R module is less than the dimension of R bar. So this thing is already an R bar module. I annihilates this thing. That's one of the properties of the Koszul complex. But what I need is that the annihilator of this thing also contains something that's a parameter on R bar, essentially. All right, and I'll talk about why I need that. Okay, so let's assume all this holds. Then we get the corresponding m-adic continuity result for R bar and its perturbations. All right, so sufficiently small perturbations, I become arbitrarily close. The Hilbert-Kunz multiplicities are arbitrarily close. And I kind of crunched another result in here. Let me make a note. The argument is actually formulated in the paper. It's for arbitrary. In primary ideals containing I. There's nothing, the same argument really extends, and it's not a big deal, the distinction. Okay, so here's a corollary, which I think is interesting. Again, I'm interested in the values of these things, and I want to understand them better. So let's assume the conditions of the theorem apply, right? And so I've got all those conditions on R mod I. And assume that R is reduced and just already complete. Just makes the statement of this a little bit easier to say that. Take minimal generators for I, then you can realize the Hilbert-Kunz multiplicity of R mod I as the limit of a bunch of Hilbert-Kunz multiplicities of radical extensions. So adjoin roots of the minimal generators to R, take the limit, and it gives you the Hilbert-Kunz multiplicity of R mod I. I actually saw Thomas and Ilya's results. This is what I was thinking when I saw that. I was working with my advisor, Ian Auerbach, on the Yoshida-Watanabe conjecture. We worked on that for a long time, didn't really get anywhere. But anyway, part of the idea was to try to do something like this, to use induction to prove something, induction on the dimension to prove something. And so my initial interest actually came from trying to understand Hilbert-Kunz multiplicity of these quotients in terms of these kinds of Hilbert-Kunz multiplicities. So this is a satisfying result, at least to me. All right, now I'm going to check the clock. That was 30 minutes. That's good. That's good. I'm going to go ahead and start telling you guys about the proof. And the idea is really to extend the basic trick that Thomas and Ilya used to rings that aren't Cohen-Macaulay. And it takes quite a bit of work, or at least felt like a lot of work to me. All right, so in order to tell you what I'm extending, I need to tell you how their proof works. And it works by first reducing to the case that R is complete. That's not tricky at all because, when it comes to lengths of imprimary ideals, completion, at least for Noetherian local rings, is really, really nice. Then invoking Cohen Gaba, this is why they need R hat mod I R hat to be reduced, so they can use the Cohen Gaba structure theorem. And when you do that, you get a diagram like this, okay? I've got a regular local ring. This is the Cohen subring. You choose a coefficient field, you choose system of parameters on R bar. Cohen structure theorem gives you this. And the Cohen Gaba version says if R bar is nice enough, then you can choose this to be generically a tall. All right, and to do that, they're using both the fact that the quotient is reduced in Cohen-Macaulay. All right, the real reason that this matters is because for F-finite extensions like this that are generically a tall, there's a way to control the convergence rate of the Hilbert-Kunz multiplicity. And essentially their argument is about trying to do that in a uniform way. So just a few words. In their setup, this guy, R bar, like I said before, it's R mod a regular sequence. Since R is Cohen-Macaulay, so is this quotient. And that means it's free as an A module, which is really, really nice. They're able to show that if I take sufficiently small perturbations, of my ideal I, it will continue to be a parameter sequence. So it'll continue to be generated by a regular sequence. So these quotients are also Cohen-Macaulay, and they'll also be free over A. It's not super hard to show they have the same rank as well. So what's the point? The point is that using this, they're able to compute the discriminants, or yeah, I guess they don't compute them, but they are able to show that the discriminants of R bar and these sufficiently small perturbations can be made arbitrarily m-adically close in A, the base ring. And as I kind of mentioned before, this discriminant, which I will speak about in a minute since it plays such a big role in this, this basically gives uniform. Gives uniform control over the convergence rates of all these guys. All right, that's how they prove this result. So they get like a uniform growth rate for all of them at the same time, and it's very easy to then prove lots of things about how they're related. Okay, so let me tell you about this remarkable thing called the discriminant. It's going to be a very brief description. Let me just say that I remember a long time ago learning about the determinant of a matrix and just being blown away by how much information that one little number contains. The discriminant similarly contains a lot of information. All right, I'll define it. It's kind of a mysterious looking number, or element of A, but let me just go ahead and do it. All right, so let's let A and S be local Noetherian rings. Let's assume A is a domain and that there's a modular finite extension from A to S. Let S1 through Sn be elements in S that become a basis when I tensor S by the quotient field of A. Okay, so the quotient field of A is a domain, it's a field. Tensoring here, I get a finite vector space over the quotient field. These elements map to things that constitute a basis for that. Right, so that's what I'm assuming. Then the discriminant of S over A is defined like this. It's the determinant of the trace of the product, the products of elements in S that are mapped to this basis. There are a lot of things in here that might be confusing looking. Let me just say that this trace is as a linear transformation from this guy to itself. This is a finite dimensional vector space over the quotient field. Multiplication by these elements is a linear map, right? And so I can represent them as a matrix even and take their trace. And then I can put all of these into another matrix, take the determinant. And sort of a priori, I get something that will be in the quotient field of A, right? So these traces will be in the quotient field of A since they're taken from matrices with entries in there. And then I'm taking the determinant of a matrix like that as well. So I have something in the quotient field. But if A is normal, you can show that as long as this is computed with elements that started out in S, you get something that's integral over A. And so it'll actually belong to the ring itself. And one of the many nice properties of this discriminant is if I that map to a basis when I tensor with a quotient field, I just get a number or an element of A that differs by a unit. Okay, it's kind of amazing, but if you just sort of work this out, you can show that there's just a nice simple relationship between these. So this discriminant actually detects generic atollness, and it's used in one of the most famous papers in characteristic P, commutative algebra, by Oxford and Hunicke in their tight closure paper, original tight closure paper, to construct invariant. So let me just say what I need to say here before I forget. This guy's non-zero exactly when this is generically a tall. I still haven't told you what that means. I'm not going to tell you what it means. It means, well, I'll tell you very briefly in a way that may or may not be interesting or meaningful. It means that this thing is a finite product of finite separable extensions of A, of the quotient field of A. Yes. What else do I want to say? I want to say that if A and S are both a finite and A is a regular local ring, in which case it will be normal, right? Then this discriminant can be used to explicitly I want to say control the convergence rate. Of this limit that defines the Hilbert-Kunz multiplicity. Okay, so this is the idea. Notice that this discriminant has to be non-zero. Okay. So my plan, I want to do the same thing, but I want to do it without assuming Cohen-Macaulayness. So notice, as I mentioned, in the argument in Thomas and Ilya's paper, R bar and these perturbations are all free over A. And so you can just choose a free basis and compute the discriminant like that. And this is a huge part of their argument to show that they're m-adically close together in A. So I can't do that anymore. So I have to do something else. And the way this works is basically, I'm going to draw another diagram here just for the fun of it. I show that when this dimension of the H1 condition is satisfied, that you can find elements R1 through Rn in R that map to a basis over the quotient field of A for all these guys. Of course, this is for really big T, but it is explicit in terms of, like, I don't know, maybe 6 Archimedes numbers or something like that. I do get about. The argument is crazy, and maybe long it needs to be. But the idea is, rather than working with these, free A modules and then computing discriminants like that, instead I find elements up in R that will constitute a basis for this, for all of the perturbations. And since they're images of the same elements up in R, that's enough to show that the discriminants are close together in A. And that gives us modulo torsion, which I won't talk about, enough to show a uniform kind of convergence rate. Okay. Awesome. I think I have 10 minutes. And so now I'm just going to tell you a bunch of results. mostly. Okay, so these are lemmas from my paper. I'll tell you the name of that at the end. Eventually, I sort of realized when I was working on this that this diagram, which as far as I know, pretty much only shows up when you use the Cohen structure theorem, unless you do some really artificial type things. But that diagram itself, when it's in play, you can prove a lot of things about perturbations in general. So I stated a lot of my results sort of with reference to this diagram, sort of with the hopes that maybe someone might find a way to use them in a different context. But let's suppose that R and A are complete Noetherian local rings. I is an ideal, and there's a commuting diagram that looks like this. I always called it diagram D in the paper. So if you read that and see diagram D, this is what I'm talking about. And let me just note something very quickly. This extension is finite, right? So that actually means that if I extend the maximal ideal up to R and then add I to it, I get something that's m-R primary up in R. Incredibly important fact. Okay, so this lemma, as I've stated here, has two parts. The first part is actually not too hard to prove, or at least I didn't think it was. So let T be any integer such that this inclusion holds. We can do that, right, because this guy is in primary. And let's let R1 through Rm be any elements that map to a minimal generating set in R bar as an A module. So these guys map to A module generators for R bar here, and they're minimal. Then choose any generators for I. They don't even have to be minimal generators for the ideal I. And any epsilons that are in this power of the maximal ideal. The images of those same elements will continue to be minimal generators for these guys as A modules. All right, this is actually not hard. Really, all it comes down to is showing that this holds. These are actually equal. And then using completeness and some stuff, you get the result. Okay, that's A. B, this one was a bit harder. This is where all these Art and Rees arguments show up. Okay, so assume that we've got, let's assume that the depth of A is 1, or sorry, at least 1, and that there's a non-zero divisor in A that kills this first homology of I with coefficients in R. As I'll mention in a second, the whole dimension of H1 being less than the dimension of the R bar in the statement of my theorem earlier is just to ensure that I can do this after I can find such a D after I use the Cohen-Gabor structure theorem to construct an A in that diagram. So if this is weird looking to you, just replace it with the dimension of the H1 property, which may also be weird, but anyway, that's what that's about. Okay, so then let R1 through Rn be any elements whose image in R bar span a free A module of rank n. So R1 through Rn become the basis of a free module when I mod out by I, free A module. Then I can choose a T, and this T depends on the diagram. It depends on the little d, which is my non-zero divisor that kills the Kazul homology, and it depends on these elements. It really depends on the A module they span, but depends on those elements, such that if I have any minimal generators F1 through FC for I, and any elements epsilon through epsilon C in the Tth power of the maximal ideal, then the image of those same elements will continue to span a free A module, the same rank, and all the perturbations of R bar. So these two things together are enough to show that the discriminants of these rings are close together. It's enough to show a bit more too, but let me say, this is sort of a complicated Art and Rees argument. I hate complicated arguments. Sometimes they're unavoidable. I tried really hard to make this less complicated looking, but it's just kind of a messy argument. You have to do Art and Rees at the level of R and R bar at the same time. And anyway, it's a interesting, if anybody could come up with a simpler one, I would very much like to see that. All right, and let me also point out that this is what the H1 dimension condition is about. If the dimension of H1 is less than the dimension of R bar, then in this diagram up here, A has got to have something in it that annihilates the H1 that's non-zero. So if A is a domain, or in particular a regular local ring, for example, then the conditions needed for B are just sort of automatically satisfied. That's the purpose of that H1 condition. Okay, so I have 5 minutes, I believe. And let me just say a couple of things. Along the way, kind of for free from the results I just told you, you can compute Hilbert-Samuel multiplicity as long as you have a reduction, minimal reduction of the maximal ideal as a rank. And taken together, these two results, A and B here, are enough to establish that the ranks of these R bar and its sufficiently close perturbations will be the same over A. And so as long as you can construct a diagram like that using the Cohen structure theorem, which technically requires that you be equicharacteristic. There are modifications in mixed characteristic that I'm not going to talk about. But if R is an equicharacteristic Noetherian local ring, I is an ideal, let's assume that the dimension of R bar is at least 1, just so I can use these results. And M is a finite R module. Let's assume that I have a corresponding condition on the H1 of M. So the dimension of H1 of I with coefficients in M is less than the dimension of R bar. Then there's a T such that I get equality of Hilbert-Samuel multiplicities in R bar and sufficiently close perturbations, right? And that applies to modules as well. Also works for M primary ideals containing I. As far as I know, this is sort of the state of the art on this kind of thing, although there's a whole lot of literature about Hilbert-Samuel multiplicity for, going back a long time. And from what I can tell, I think this may be the strongest result of this form, but there are other results like this that have been known for a while. And some additional ones that put other constraints on I or only apply to certain generators and so on. Okay, so I think that's a good place to stop. I've left a little space so I can answer questions maybe. Thank you.
All right, let's thank Nick.
Thank you very much.
Are there any questions for Nick?
So I have a question.
Sure.
Maybe it's a little naive, but after you showed us your main theorem, you first showed us a corollary that said something like to compute the Hilbert-Kunz multiplicity of these quotients,
Yeah.
take limits of adding. Is it possible to use this to maybe actually compute some Hilbert-Kunz multiplicities?
I mean, that's not a naive question at all. That's something I would love to do. But the trouble is, even computing these is incredibly difficult. So I think probably there might be some way, but I haven't found some amazing way to make an impossible Hilbert-Kunz multiplicity somehow possible to compute using this.
I guess the naive part of my question was that I'm kind of ignoring like how crazy difficult to compute these. would also be.
I mean, I agree. I would love to use this. You know, there are results about limits of rational numbers being irrational or transcendental. I'd love to use this to show something is an irrational Hilbert-Kunz multiplicity or something like that, but I haven't been able to figure out any way to do that.
Thanks.
Can I add one thing to that?
Sure.
Thomas.
Yeah, so Eloise, just to also, so Paul Monsky, a huge chunk of his career could also be thought of as being devoted to just computing Hilbert-Kunz multiplicities of some hypersurfaces.
Yeah.
So yeah, they're very difficult.
He's a very clever guy too. So yeah, that's
Very much so.
Well, but maybe he didn't have all the tools.
true. Let's hope, you know, I would love to do that.
Corollary before, right? So there's a chance that maybe this can help.
I wonder if he knew that though, or suspected.
So Ian definitely had some suspicions about this. So the idea that you could do something like that corollary was known, at least to some of the people in the field for sure.
I'm curious about, so the final theorem that you stated about the Hilbert-Samuel multiplicity. So you said that you need the ring to be equicharacteristic in order to use your machine.
Yeah.
But is there another proof that doesn't use your machine? It doesn't
That's a good
need equicharacteristic?
I would be interested to know. I think basically the machine will work if the residue characteristic is a parameter on R bar, basically. I think that might be the most general form, but I'm not sure. I'm definitely no expert in mixed characteristic stuff.
Sure.
Yeah, I don't know.
Can you take your proof and do a perfectoid version of it?
That would be cool. I don't know the answer to that. I'm very far from knowing the answer to that actually, but yeah.
I'm just hurling words around.
It's a cool word. I like it.
The other question I have is, earlier you said that if you had time, you would talk about some examples that you have in your paper that show the limitations of the assumptions. I love these examples.
Let me show you some examples that I stole from Thomas's paper with Ilya. Yeah, let's see. So originally, or at least naively, I had hoped at some point that maybe I would be able to show that not only was there this m-adic continuity for Hilbert-Kunz multiplicities, but maybe they were just all equal eventually. And it's a weird invariant, maybe something crazy like that happens, but you can show that that's not true. So let's see, let's take F to be X times Y inside of this power series ring. And a field characteristic P. You can show that the Hilbert-Kunz multiplicity of, let's call this guy R mod F is 2. The associativity formula gives this to you. However, if I perturb that by powers of Z, I get this. This is I guess this is an AN singularity. All right, and there's some formulas for really nice singularities like this due to Watanabe and Yoshida that allow you to compute this. So these are all distinct. And even more interesting is like, these are all distinct primes. So all of the perturbations of F, like all the perturbations of F like this are prime. There are infinitely many prime ideals that are perturbations of F. That also kind of killed some conjectures that I'd come up with in the course of writing this. So, yeah,
I think
there are some
aren't they
other great
all-
examples too.
They're all even
Oh,
strongly F regular, probably.
Yeah,
Like
I
they're-
think so.
They're really
They're
nice.
Yeah, they're rational singularities, I think, and they're Gorenstein. So
So you can get arbitrarily close to a not even a domain from strongly F-regular rings.
exactly. Anyway, this is it's a fairly simple example too. So I'd be willing to bet that this is not an unusual type of thing to occur.
Cool, thank you. Other questions for Nick? All right, hearing none, let's thank Nick again.